carry skip or carry select, we arrive in logarithmic solutions. Now, even though they are all logarithmic, there is a fundamental difference between them, and the constants which we do not take into consideration in asymptotic notation will make a difference in practice. And we also briefly discuss about kind of, hybrid solutions, and this is, it just happened that I stopped here, and this is a kind of strange solution if you look at it. It is a cascaded adder of carry look-ahead adders. Now, do you see any advantage of this? Why would that be good? I mean, this is a 48-bit operand. And if I want to go for speed, I would go, for look-ahead or maybe for prefix. But what I'm doing in here is I'm cascading 3 look-ahead adders. Then this is ripple between those. And each of them is look-ahead adder. Why would that be a good solution? Yes.
Less circuit. And so
the lesser circuit that I can build, it's a ripple carry
so
adder.
less cost to performance trade-off.
Then it's a trade-off between cost and performance, because now I ripple over look-ahead adders and not over full adders. But there is something else in it, because this is not very deep. Will have not that much energy consumption. I will not go too much down and return. But that kind of things you have to consider carefully when you make a design. And even though such a solution may not look very interesting in general, it may be applicable in certain situations. And there are many possibilities. Essentially, if you take all the ingredients that you put them in a shaker, you mix them, you may get, whatever the dice will give you. Now, essentially, last time we stopped here. And this is not a general discussion, but it applies to a special class of adders. When you do multiplication, you start with 2 operands, then you generate a partial product matrix. It's like when I'm multiplying 11 with 22, I say 22, 22, this is the partial product matrix, and then I have to add them. Okay, there is no carry now, but I'm happy because my number is nice. Now, if you look at what will come out of this addition, you see that the least significant part is coming early, and the most significant part is coming a bit later in this reduction. We'll discuss about how to do that reduction in just a second, maybe a couple of minutes. But essentially, in a multiplier, what you have this, which is the partial product matrix, and then you reduce that to 2 rows, and then from 2 you reduce it to 1 row with an adder. Then this is a normal adder. Now this adder, as opposed to adders which are normal in a processor like in an ALU, which do get the operands from the register file in the same time, most significant or least significant bit, they get the operands in that kind of order. Then those are coming first and this later. Now this is opening some possibilities for optimization, because I should not try very hard to do something with those bits, because I don't know them yet. And then what I'll do, I will concentrate to do the calculations until let's say to this moment, to the half of the adder, as fast as possible, and to be prepared to complete the calculation when this part is coming too. And this is a different technique of making adders, and this is an optimization which is specially for adders which are part of multipliers. Now, this is a comparison which which is telling me something about the energy consumption and the delay of an adder. As you see, there is a trade-off between the delay and the energy consumption. I can look, let's say, to this link adder. You see, if I am allowing for a longer delay, I will explain you in a sec what this means. Then if the delay is longer, the energy is lower. If I am pushing performance to get, faster calculation, I spend more energy. And what you see to the link, this is getting exponential. This is not nice. And this is essentially due to the look-ahead structure, which is generating a lot of glitches due to the down and up traversal of the tree. If I go for prefix stuff, this is getting a bit more linear. The conditional sum, it's even nicer. And depending on what I want to achieve, in my design, I will select one of those, and I will also understand the relation between cycle time and the energy that I'm consuming, having such a graph. Now, this is a very good tool to characterize technology and to make the right decisions when you design a processor. Now, this diagram is obsolete in the sense that this is a very primitive technology. It's 130 nanometers. Today, this is obsolete. And it's also high voltage, I would say 1.2 volts it's not what we use today in high performance processors. But the tendency is the same. Now, this is an analysis which is not done by real implementations and measurements for each and every point in this diagram. This is based on a method which is called logical effort. And the logical effort is trying to make a bridge between underlying technology and the structure of an adder of a circuit. And is based on the following assumption. You compute the delay in terms of what is called an FO4. FO4 means the delay of an inverter in that technology. Then I have an inverter which is driving now 4 loads. Then in order to do that analysis, what I'm doing, I'm taking my technology, I take an inverter, I apply 4 loads on it, which is a capacitive load, which is 4 times the capacitive load of a gate input. And I am doing SPICE simulation of this guy. Based on the SPICE simulation, I determine that number, and I can tell you now, if I have that number, I can tell you exactly how much will mean this 9FO4 delay in nanoseconds. And I can tell you something about the performance. That's from one side. From the other side, I take the network of the circuit at the gate level, and I'm computing the delay, the critical path, in terms of equivalence of FO4. And this allows me now to make an abstract characterization of an implementation, which is not yet in silicon, and to get something from the technology which will help me to really evaluate the performance of such a thing. And I can repeat that from any technology I like and please. This is called logical effort, and you can even apply it for energy. It's not that straightforward, but there are methods to determine the energy consumption also in a bit of abstract thing. No. We give priority to the people behind.
You said that the inverter is driving a load of capacitors?
Of 4 inputs, gate inputs.
4 gate inputs. So each of the capacitors is over there that you've drawn. Well,
I didn't.
Drawn.
Okay. Then essentially what you do, you assume that this is driving a gate, this is driving a gate, a gate. This is one of the inputs.
So in total it's 4 gate capacitors that
Yes.
you have to drive.
Then essentially this is kind of a typical case in a circuit. That's the reason why you choose that. If you characterize in inverter delay, most of the time you will have more gates which are driven by one inverter. And then based on some studies, the guys which proposed the method, they said, this is the representative utilization case for the inverter. Okay? Clear? Crystal clear. And you?
I was more curious about the
You are
fan out
always curious.
4 because we drive most of the times like 4 gates. It's like
No,
less times,
depending on the circuit, you know, they made an analysis and
it's
you know statistics,
Yes.
you know,
Heard of it?
lies, them lies and statistics. You don't know that code?
No.
No? In life there are lies, them lies and statistics. I don't remember who said that, but was somebody important. Essentially speaking, he was right, because statistics may actually tell you the wrong message. If you do them right, they reflect reality. But if you don't do it in the proper way, they give you wrong signals. It's okay? Now, when I want to make a choice for a design, I have to look in such a diagram and see which is best for my boundary conditions. Now, this is a beautiful diagram, which I will not get into many details. I even don't know if it is treated in the book. This is trying to make a classification of adders from the point of view of 3 parameters. The number of logic levels, which is essentially the thing which we mostly look at. Remember, we are speaking about prefix adders, and I said this is better because it has 5 levels instead of 7. But also the fan out of the gates is important, and also the wire tracks. Long wires are problematic. And this is trying to make a classification of that. Actually, if you look in today's technology, there might be even a new dimension. I don't know if you've heard about 3D integration. Then today I can stack chips. And there are products, you know, like my watch. You know, I have a watch and another watch in the top. You can do the same with chips. You stack them, and then you can grow what? You don't see it? It's 3D.
It is.
It is 3D. I have a watch here and another watch here.
The question is why?
The question is why? Because it's beautiful. In this case. But when you do that in silicon, there are advantages. And, you know, one of the advantages of 3D technology is the following. I have a very large adder, because we talk about adders. Eventually, I have very long wires going on here, like that. If I split it in half, and I fold it, and then I get 2 chips in this way, the longest wire will be half length. And I will have possibilities to connect those with what we call TSVs, through silicon vias. Do you know how PCBs are done? Printed circuit boards? The same story. But now instead of having metal layers and vias, you have silicon with chips, you know, with diffusion, epitaxy, metal, oxide, whatever, and you connect them in this way. And now if this is not good, I can make it like that, and I can make 4 of those. Then I have a new dimension in the design space. Traditionally, we have a 2-dimensional space, then my chip will stay in this Cartesian system, and now I also have Z. You know, this was invented by Descartes. Do you know where he did invent it? This? No? Descartes was not Dutch, but he lived in the Netherlands for a while. And he had a problem with distance. You know, in the Netherlands you don't really have hills, but things are going a bit up and down. And he wanted to compute the distance between 2 points. And then when you just look like that, you don't really get the idea. And then he came with this Cartesian reference system. In Delft, by the way. Okay. Not in Eindhoven, sorry. Or in Prague. It happened here. Even though I think you have higher hills in that area. Kind of thing. Okay. The last part on addition relates to modular addition. And when I have modular 2 to the power k of 2 to the power k minus 1, things are simple. I drop the carry, or I drop the carry and do an end around carry. When I have modulo 2 to the power k plus 1, I use an overhead. Then instead of using k bits, I use k plus 1 bits. And then I use a different representation, which will still allow me to do simple calculations. But remember, 2's complement, 1's complement moduli are beautiful, but they are not delivering the trick. Then if I really want to take advantage of the RNS, I should go for a general purpose modular adder. And that's the way general purpose, somebody criticized me some time ago about that. You did? Okay. You see? I have memory. Still.
Now if only you could just put it to full screen again.
Okay. You know, errare humanum est. Yeah, we cannot be perfect. But if you want that, it may happen. I should even learn the command L. Now, there is a general recipe on how to do a modular adder. And this is the general structure of it. I can do it in 2 ways. I can say I do first the addition of the 2 moduli, and then I see if that is larger than my maximum value, I subtract the modulo from it. That will take me 2 additions. What we do is we use the principle of anticipation. Because I am rich enough and I have enough area, I will do 2 things in parallel. I will consider both cases in the same time. I will do the addition, but I will do also the addition minus the modulo. This will take me slightly longer, but not much longer. Because what I'll do first, I'll take the 3 numbers, x, y, and the modulo. I will compress them to two numbers with full adders, which are working in parallel, and then I do an addition. Now, based on the result of this addition, depending on the sign bit of it, I can select this value or this value. If this is negative, it's not good, because I try to subtract too much. And in this way, what I am doing is I'm computing the modulo for any type of moduli value in the delay of one addition. Then I manage to hide the second addition delay by doing it in parallel, and what I have as overhead is the delay of a multiplexer and a full adder in the top. Is this scheme clear? Yes?
I don't quite see why that carry save adder is so much faster than...
Because the carry save adder, I think we discussed about that. There is no carry between the things. The carry save adder is a string of full adders which are rewriting 3 dots into 2 dots without doing the propagation.
Right. Okay. Yes.
Okay? Then it's the same delay plus a full adder and a multiplexer. Then this may be significant if I am on the limits of the clock frequency, or may not count if I still have some room in the determination of the clock frequency. I'm not sure if I said that in the computer architecture class about how we actually dimension the clock frequency. Even if I did, you will say I did not, right? Hmm? Yes? You cannot hear us.
Yes.
Ah. I have no battery. There is a bit of battery, but not much. It's almost empty. No, it's almost empty. I don't think it will hold until the end of the lecture. Hopefully it will. You know, it's blinking. Oh my God. Okay. Where was I? That.
You want me to go bring some batteries from the...
If you run
I
fast,
run fast.
just to, maybe they can give you another one. Just 1 minute. You know, energy consumption, bad design, or maybe bad management. Yeah. He's trying to bring a new dose. Okay. Now, then practically we cover the addition and we can finish the course. Because we know how to represent numbers, we know how to do addition, then we can do whatever we want. Then I can close the shop, go home, and see you at the exam. This is true and is not true. It's true in the sense that what I said is correct, but I did not take into consideration performance. And what we'll discuss further is how to improve the performance of multiplication, division, because if I straightforward rely on addition, I can do them, but it will take longer. Then if addition takes 1 cycle, and I am doing multiplication based on addition, it will take n cycles when n is the number of bits. While in normal processors today, multiplication takes 2 cycles. Then in order to get 2 cycles multiplication, we have to put some effort.
If it still doesn't work, just give me a call. You can go.
Okay. I have to be strong engineer. This is a good example of Southeastern Europe collaboration. Right?
Right. And Middle East, a bit.
And Middle East.
Don't forget.
Yep. Apparently it's okay. You can hear me? Yeah, brilliant. Okay, thank you very much, sir.
No problem.
Ευχαριστώ.
Παρακαλώ.
You can learn a new word, how to say thank you in Greek. Ευχαριστώ.
Παρακαλώ.
Okay.
You'll make no use
You
of
don't
this.
have to answer back all the time. Okay. Now, I said that if I know how to do addition, I know how to do multiplication, and I can do all the things I like in place. Essentially, we look in this problem. I have k numbers, which are n-bit numbers, and I want to add them. Then I have a series of addition, not additions every now and then. With a program, I can deal with that. But the question is, how can I improve the performance? And as I mentioned a bit before, multiplication actually relies on a multi-operand addition. Then I first generate those partial products, and then I have to add them. When I do it with pen and paper, I can add those guys, and then I can determine the transport and things like that. And I will inspect them from this significant bit to most significant bit, and then I'm done. In a kind of algorithmic approach, what I can do is to take them two at a time, then I add those, I obtain a result, I take the result of those, add with this, a new result, add with that, which brings me to a sequential approach towards multi-operand addition. The fact that this is not rectangular doesn't matter. In here I have zeros, and in here I have to do something to deal with the sign. We most of the time do sign extension. Remember when I was discussing about those complement numbers, and we said that you have to sign extend because otherwise the value will not preserve? Then if I add 0, 1, 1, 0 with 1, 0, 0, those are in two's complement. This is a positive number, and this, if I look at it only at 3 bits, it's a negative number. If I want to preserve the value, I have to repeat the most significant bit. This is called sign extension. You look at me like you never heard about that. And I'm pretty sure you heard because I discussed about it. Then basically on that part of the matrix, I can do sign extension. Okay, now this is the straightforward approach. I take two numbers and I add them pairwise one at a time. It's very much like the bit serial addition. But now the granularity is not at bit level, but at operand level. There is, however, something which is slightly different. While I'm accumulating numbers, my result will be representable on more and more bits. Then I have the k bits, which are it's the dimension of my operands, and while I'm adding them, I add more bits. Then my output register or my output reservoir where I store the result has to be able to accommodate that. Now, given that my maximum value is the value that I can represent on k bits times the number of numbers I have, then it's, I don't know what is the maximum value on k bits, but you can tell me, multiplied by n. You are not with me. You think at Carnival. It's next week. Then I add those numbers, and in order to represent the sum, I need more bits. How many more bits I need? It's the logarithm of the number of operands. You can check that very simple. Can you? No? Why not? How many bits do I need to represent a number with value m? Log m, roughly speaking, is actually the same. Then the maximum value that I can represent is the value that I can represent on k bits, which is 2 to the power k minus 1, times n. That's the maximum value. Now, if I want to know how many bits do I need for that, I compute logarithm of that. It's okay? And logarithm of that will give me k plus log n. You look very annoyed by these silly mathematical simple calculations. Not all of you, but some of you have a face which is like, why is he talking about that? Okay. Because of this serialization, what you end up in having is a time which is in this complexity. Then it's supralinear in the number of operands. And this is certainly something which I don't like. I mean, I should be able to do it faster. If I'm not doing faster, then I have a problem. How can I get to do multiplication into cycles if I rely on this accumulation? Okay, then if I apply this trick to this, then my multiplication will not give me good things. Now, one way to do is to try to use more adders, and this is a combination of more adders and some kind of pipelining, and because of the fact that you have to add good things with good things, you also have to delay them. This is not very simple to grasp, and it's not really giving you a right solution. It's just, I would say, a bit of a puzzle. And the puzzle of Barhami is that how come that I get a speed up of 4 on this scheme? You can trust me and him that you get a speed up of 4 by only using 3 adders instead of 1. My intuition is always that if I double the effort, I may get half of the delay. Then if I put more effort, my results are better. Now what I put here is 3 times more hardware, and I get 4 times more performance. Roughly speaking, do you have an idea why is that? Because the answer is very simple.
Yeah, adding hardware unit doubles the performance.
Yeah, but that's the question. It does not. Because I am triplicating the cost, and I am getting a performance which is 4 times better.
The third adder is used with feedback.
Yeah, because I have to accumulate numbers.
Yeah.
No, just look at it as a principle. Then I use 3 adders instead of 1, and I get a performance which is 4 times better. What I am doing is I'm accumulating numbers. Those are pipeline adders, as you see, they are in stages. And I am applying delays in order to have the right data flow. And at the end of the adder, I'm feeding back, the partial result in order to get further into accumulation. At the end of the calculation, in here, I will have the right result. The answer is simple, because you are trapped by something which is not relevant. The number of adders is not relevant. What is relevant is the number of stages in the pipeline. When you put a pipeline in the processor, what do? You improve the throughput. Because you have 4 stages, your throughput is 4 times better. That's the same story here. The fact that I have 3 adders is just making this scheme to function. I can use also 4 adders. Then, is it clear what I just said? Also for you, sir. You have a face which is kind of telling me that is not clear.
No, this is clear.
It's clear.
Yeah.
Then look at me and smile.
Okay.
I need to get feedback, right? If I'm preaching and you are not reacting, then I'm frustrated. Okay. Now, what do we know? Remember, when we have a problem, we build a tree. This is a kind of cookbook. When I don't know how to do something and I want to improve, I have a couple of recipes that I can use. And one of the best recipes that I can use is to make a tree. Because when I make a tree out of n operands, I will have a depth for the tree which is logarithmic in the number of operands. Then my expectation will be that if I make a tree like this one, let's say, I have k-bit numbers, n of them, and I am adding them pairwise. In the leaves, I have more parallelism, and while things are going, deeper, in the tree, I'm getting less parallelism, and eventually I arrive into the root of the tree, where I make the final calculation. Then, my intuition is that this should deliver good results. And it should deliver good results because I have parallelism, and eventually now I get that kind of complexity. Because will be the log of n, which is the number of levels, plus some kind of extra overhead. Then it's logarithmic, while previously, now this is also a bit of a tricky discussion, which probably is good to do it. I have now two parameters, and depending on which one is the larger, I can focus on this part of the asymptotic notation on this part of asymptotic notation. When I was speaking about asymptotic notation, I was speaking only about one parameter, and I said the factor in the expression which has the highest power will be the one which counts. Now, because I have two parameters, I have to consider both. If this is small, this will be the dominant factor. If n is large, this will be the dominant factor. But doesn't matter how I do it, it's better than this. Because what I did is I don't have this factor here, and instead of having a product here, I have a sum. Okay? A product is always giving larger numbers than the sum when you apply it to the same operands, right? Or not. Is this true? What if they are fractional numbers? Okay. Then this is what I get. Now, what do I see here? Before I go to the next slide, it's better to comment on something. Now, what I'm trying to do is I'm trying to make each level as fast as possible. Because the faster the level, the better the delay. The number of levels in the tree will depend on the number of operands that I have to add. And this is something I cannot change. But I can focus on the others and try to make them very fast. That's something which I didn't say. You see the dimension of the adder, it's increasing while getting closer to the root. This is due to the fact that while accumulating, I need more bits to represent the value. Now, there is a trick in here which is counterintuitive. If I use, let's say, carry look-ahead adders or prefix adders, which are very fast, I will complete the addition of the numbers in a log k time, and the next adder will wait log k time and then can do the work. However, if I think about ripple carry adders, I can get an advantage. Why is that? Because if these two bits are added in a ripple carry adder, the result is already available here and here, which means that these two bits can start the processing immediately. This will apply also for this. Then after 1, 2 full adder delays, this can also start working. Then while in standard addition, ripple carry adder is not a good solution, in this situation, ripple carry adder is actually a good solution because it will allow me to overlap between levels, between the working of the levels. And this is the drawing that you have here, and you have a zoom in the story. Then because those guys are working, you know, they generate results, and then while this is doing the work, this is also propagating, and then when I get into the second position, I have all the things done, and in this way, I can get to a faster construction. it's still, as we said, logarithmic in n. And there is a kind of constant which is giving there, but now the constant is nicer than, from the point of view of the asymptotic notation, I didn't do anything. Because it's still k plus log n. From the point of view of the effort, hardware effort, I won a lot. Because now I just have a sea of full headers, which are connected in this way, you know, they have carries people in, and also there are things which are transferred between the levels. There is a propagation, there is an activity in the system, which is now going like a wave. Then things are propagating in this direction in the same time. And this wave will complete things faster. Yes?
So instead of using 4 ripple others, we can use one other for one ripple carry other in the other space. So to compute the first other's result, we need 4 ripple carries, right?
No.
Well, let's say 4. I mean a number.
No, I just need a ripple carry header.
1.
When I say ripple carry header, it's an n-bit ripple carry header, or k-bit ripple carry header in my case. Then in order to add the first 2 numbers, I have 7 numbers here, right? I take 2 of them and I apply an header. This is a k-bit header.
Yeah, I'm saying that we can use only a 2-bit other in each case, not a 4 2-bit others.
But we don't, I don't understand what you want to say.
I'll ask later.
The phenomenon that I want to push on is the fact that in a counterintuitive way, trying to optimize locally, it will give you a bad result on the global sense. And this is true also in other situations. Then a local minima does not guarantee a good optimum on a global space. But in here, it's something which relates to the information flow, is the data flow, which in ripple carry headers will unlock the information for the next level before the completion of the calculation. Now, this is the best I can do, and this is the best I can hope. Because what I want, remember I'm always saying that, what I love is logarithmic complexity, and because I have 2 parameters, that will be good to achieve. And we can achieve that by relying on carry save headers, which we will discuss. Okay, we can discuss about that now. Then the first design is a ripple carry header. What the ripple carry header is doing is computing the sum and the carry for each position, and this is moving until the most significant bit. And this is the dot notation of this guy with the carry in and the result. What the carry save header is doing is postponing the calculation, the explicit calculation of the sum, by representing the number as 2 numbers. Then I am taking my operands, and instead of propagating the carry over the header and producing 1 number, I will produce 2 numbers. One will be called the sum, and the other one will be the carry. Then while this guy is taking those numbers and is propagating until here, and the delay of this calculation, it's proportional with the number of bits. If I apply the same technique, but now instead of reporting the carry to the next position, I will report the carry to output, then like in the second drawing, you see now the full headers are not interconnected. I can have 1, 2, or a million. They will work in parallel, and then the transformation of 3 numbers into 2 numbers will happen in parallel without having propagation. And this is what is happening? Then I have this, in our case, we have 3 inputs now, you see? Then I can accommodate 3 operands. Then I take them and I process them in parallel. And then instead of adding the carry to the next position, I will store it here. Then I have a number which is called the sum and the number which is the carry. My actual result of the addition is conserved because this plus this will eventually give me the same number based on the fact that I conserve the value in this transformation. However, instead of having a logarithmic, actually this is a linear delay, as in the propagation, in the ripple carry, I will have a constant delay. And now you can already see what the idea will be to do multi-operand addition. I take those numbers in pairs, and I can do that kind of reduction. I can do that serially or in parallel. If I do it serially, my cycle time will not depend any longer on linear or logarithm of n, will just be a full adder delay. If I do it in parallel, you will see I can get even better. And that's the beauty of carry save addition, which is postponing the propagation until it's really, really necessary. And that will be necessary when I add the last 2 numbers. The previous value, which I accumulated, with the current value, I obtain now 2 numbers, which they don't make sense because I want to store them in a register and decide something based on that result. And then I would have to apply a carry propagate. We'll discuss about that after the break.